Hi everyone, thank you for coming to my talk. I'll be going over LLMs don't hack the guess, and this is from building offensive AI or using LLMs to bug hunt in environments with large code bases. Thank you all for coming once again. If you like the talk, I did it. If you don't like it, Claude did it. So I hope you like it because Claude maybe might have not done it. So here's a quick introduction. I'm an offensive security engineer. I work at Robinhood, which is a brokerage for stocks, crypto. They're mostly in the States. They have credit cards, banking, retirement accounts, a bunch of other cool stuff. I wanted to be a little extra, so instead of OMI, I did a long ID command. But anyways, yeah, I like to build and break things, and when I'm not on a computer, I go out and hit the gym or box or anything outside. And so, yeah, like I said, the inspiration behind this was I worked with, for the past maybe like 6 to 8 months, I've been using a lot of AI to try to find bugs, and throughout the experience, I've found ways where it's been really good, it's been kind of okay, and it's been maybe not so good. And so I'll start by going over examples. And first I'll go over what a complex code base looks like, what it looks like to hunt bugs with AI, and if you're in trouble potentially now or in the future, and then if you are currently using it, how you can improve it a little bit. And so complex code bases, it's no one really understands anything throughout the company, right? So when you have one with multiple thousands and thousands of dev working on the same product, there's different languages, they use gRPC, REST, queues, bunch of assumptions that may or may not be documented. And so a lot of times you end up with dozens of microservices and each of them having millions of lines of code, where it would be a point where there would be not a single person that would know what's going on, but collectively you come together to build something as a whole. And so I'll also go do like a super brief demonstration or explanation of what an AI agent looks like typically. So you have your goals and tasks that you feed into it, and this is things that you want it to accomplish, and it ships with some sort of a system prompt. In this situation, it's basically like the instructions for the agent, so what it's going to do, how it behaves, and things like that. And then over here it has memory, so this is like things it remembers, either it's stateful or stateless, and then you have tools it has access to, such as it can make web requests, it can write code, maybe it can access a database, or it can have access to MCP servers, so it can accomplish your task. And so I'll give a quick capabilities of what this does. So typically you have your LLMs that they run, and these are trained across web crawls. And so they've looked at source code repositories, and they've built their knowledge from security blogs that they've read, maybe CVE databases, exploit write-ups, as well as boxes like OS Juice Shop or the Hack the Box write-ups. So when you've seen people running these agents on OS Juice Shop and it happens to find all the issues, there's probably a reason why. So first I'll start off by going over simple examples, then I'll go over the things that it does catch, and I'll go over the things that it doesn't catch. So if you see something that's super simple, like a pickle.loads, an AI agent can spot this from miles away, and that's because it's seen this multiple times, and it's read about this hundreds of times in all the blogs and write-ups. And so if you have a simple 2 lines of code, yes, it can catch it, but it can actually go and catch it even in something that's a little bit larger than a couple of lines. So I wrote a code base that has approximately 5,000 plus lines, built functionality for auth, posting, comments, notifications, dashboard, admin panels, profiles, an API, and it's about 5,000 to 10,000 lines of code. In there I hid a pickle.loads. It took Claude code maybe like 2-3 minutes, and it was pretty easy. It found it, which meant that if you have something small enough or medium-sized where it has the ability to look through it all, it'll find it pretty easily, and that's because it takes a look at what you have and it compares it to then find patterns that it's been already trained on. And moving on, if you have something dynamic like Burp AI, I'm not sure if you guys have used it, but it basically looks at your request and sees, have I seen this before and what is most likely to be vulnerable? So in this case, it saw the object, and it's like, okay, well, this looks like something that's serialized. It sent it back. It's like, okay, maybe it's Python. And then a few back and forths later, it took maybe like 2-3 minutes again, and it was able to spot this bug. And so this is kind of how it works. Have I seen it before? What's most likely to be vulnerable? And what does this actually look like? What Burp AI does isn't something mind-blowing or crazy. It's actually just something that's a pretty simple for loop. Why it's not exploited, you find it, you fuzz it, you look what it's doing, and then you send it back and you keep trying it over and over again. It's a little bit smarter than a fuzzer, but because it looks at the output and then uses that to process it back and send it again. And so the other thing that I find it to be pretty good at is to do things that is repetitively. So if you do any sort of traditional pen testing, that's a little bit deterministic in a sense that you have run a command, you basically gather the output, you look at the output, it's either simple, or it either understands it or it doesn't understand, and then based on that, you run an exploit. And so this is capable of doing things that are simple, such as like easy VMs on Hack the Box, Proving Grounds, or it can do config-based checks pretty quickly, but the thing it doesn't necessarily do is edge cases. So for example, if you're in an environment where normally it wouldn't work, but the environment has something else that can make the exploit work, it wouldn't typically know to look for that if you're running it based on a set of tools. And the reason it won't be is because in all the write-ups it has ever read, and when it crawls through the web, most of the times it's not vulnerable. So it will rather give you the answer that is more probable than the answer that is always correct. And if most of the time something is not vulnerable, it won't prompt you back and say, okay, it might be vulnerable. So I give a few simple examples, but does that mean you should be worried? Is leadership going to come one day and say, hey guys, we don't need you, no more security engineers, we're gonna replace them all with AI? Well, I guess my opinion of AI is,
sometimes it may be good, sometimes it may be shit.
So
Sometimes
I'll go over a vulnerability that it didn't catch, and you'll understand why it didn't catch once I go through. So here's I'll be going over Helm, which is a package manager for Kubernetes. It's similar to how apt works on Linux, and basically when you have packages, the applications, they're packaged as Helm charts, which are folders of configuration files, and a chart has things that a web application needs to run, such as a database or cache or a message queue or anything else. And instead of installing each component separately, Helm just packages it together. So you basically ship it, and then it's the entire thing together. And so there was a vulnerability in Helm. There's a CVE associated with it. It's patched now. But the gist is that the attacker controls a file called chart.yaml that it basically sends to Helm and runs a dependency update command. Once it runs this dependency update commands, it touches disk as a chart.log file. And if this is symlinked, you could basically have anything in chart.yaml that gets through the symlink file to bashrc or whatever you point it to, effectively giving you RCE over the environment. So next time the shell starts, it runs the attacker's code. This can be used as an initial access TTP for any companies that have a macOS environment or a Kubernetes environment, and you can gain access over their CI/CD pipeline or their workstation or anything. And so this bug, when you actually span it across the code base of Helm, goes through about 20 layers. The source is at the top, which is the update command, and the sink is at the bottom, so 20 layers of code. And when you run it through AI, you would expect it to the files to talk to each other, maybe consolidate together, then get sent and get back with a response. However, it doesn't always work like that, and because it sends them and doesn't think of them together as one function, it failed to find this bug. When I sent this to Cursor, I gave it find security vulnerabilities with the exact line number, and it found a few false positives. It found a symlink there with Claude as well over here, but it didn't find a lot of the bugs that were associated that made this exploiting this possible. And so Claude and Cursor are my two more popular tools that I use that are built into the environment that I have. And then this cost me about 65 cents that all went to waste. It was a few lines of explanation that it gave when it found these bugs of what it thinks it was. And at the end of the day, it was just pattern matching a few lines of code or a bunch of lines of code. But then you would say, okay, maybe it found a couple vulnerabilities with Claude or it found a couple with Cursor. And let me tell you the type of things that I've noticed it typically finds that are false positives that may not exist in the environment. The most popular scenario is when data gets passed through borders like this in an environment, and in LLMs will almost always flag this as IDOR because it realizes that, hey, it's retrieving request from a microservice, sending it to another one, and it's using it to retrieve SSN info. So it's like, hey, you're taking something from user supply parameters. This is bad. You shouldn't be doing this. But if you look at the architecture, there's a lot more layers in between. And maybe it's not in this specific example, but most environments might look something like this, where you'll have a lot of random microservices talking to each other, and the chain will go through 10 or 20 files. And throughout this entire thing, there will be maybe 5 layers deep, it'll check for something. But the Claude code isn't going to automatically know how many layers to go through. And so it will almost always say that it's vulnerable because it's using it on a smaller subset. Again, back to pickles, because I love them so much. Here's a false positive with pickle.loads. So as I mentioned before, it trips out on vulnerable syncs. So in this situation, I'll give something that goes through a few layers again. You have your attacker pickled bytes that go through a decode string, and this typically here will kill the chain, so it's not exploitable, but then it'll keep going down with pickle.dumps, stores it in a database, it retrieves it from a database, it'll again run pickle.loads on it, and then you have a string object. And so typically this will go through not more than a file, it might go through a couple of microservices as well. But the moment you have Claude code look at, hey, it's taking from database, it's retrieving, it's something in a database, it's retrieving it, it came from the outside, and it's been run pickle.loads on it, it goes crazy. It's like, look, that's the one, you gotta catch it, sev1, call everybody, stop everything you're doing, sev1. But the reality is, it doesn't happen. And so a lot of times, finding bugs is just hard. On the left here, I have something that looks like a call tree, which is every function that a call would go to. So now, if you take a simple entry point, like a post API order endpoint, it's one endpoint, you use it to buy something, and over here we have a user ID, item type, quantity. It might follow a specific path in that call tree. If you change something so small as a user from a regular user to a business user, it might take a completely different path that doesn't follow the same issues. And so in this case, for example, just by changing a regular user to a business account, now it might take wholesale pricing logic. It might take tax handling differently. There might be a new credit limit checks for the account that's in place. You go one step further and you change to digital, now you've completely bypassed the inventory service, because digital products don't typically need something that requires inventory. Now you have to enter a completely new microservice, which is your licensing product. And then fulfillment of this looks completely different again. Now, this is just for buy products. Imagine what would happen if you switch this from buy to sell. It would take completely different call chains. And so this is why doing it through dynamic testing would be extremely difficult, because you now expect an LLM to predict the different paths that the parameters would take just based by changing the logic. Additionally, you can't always put a user ID in a parameter. Sometimes you have to log in as that. So now you need to have an account open for every specific user ID, for every capability, and then have your Claude code, Burp AI, anything that you use to go through and basically try brute forcing every single one. If you guys have a lot of money and you want to throw it at it and keep trying, maybe one day you might be successful. Who knows, it might be sooner than you think, but as of today, that's why I had the date actually on the first slide, because I noticed that things change so quickly that if someone were to watch this 6 months from now, they'd be like, this guy doesn't know anything. So that's actually why I had the date, because the things that work now didn't necessarily work a few months ago. So maybe you might be surprised, and maybe you might be smart to actually figure that out and go through the entire chain. So that's why dynamic analysis was hard. Now I'll kind of go through why static analysis is a little bit difficult as well. So you take, again, basically to do static analysis, you make one small change and it will take a completely different code path. And so that would mean that for you to be 100% sure, you would have to look through all the different paths in a call tree that it would take. And so typically what this would do is, I mean, let's just say you have a file that does action A, right? And it completes one thing, one item, one task. For you to be sure that it's not vulnerable, you would have to go through the entire file and have every condition be true. So you could possibly go through every if statement and every function. When you go through functions, there's also functions that go externally to other files. Then you'd have to go to the other files and then go through all of those. And then they have functions that take you to other files. And so as you guys can tell, for you to test an action symbolically, you would have to test every possible situation, go through every possible file it could talk to, and it would just result in a long list of sources and sinks that it could possibly touch. The other reason why it is also difficult is that LLMs hit something called a known failure mode, which means that they don't really say they're wrong. If you ever try talking to an LLM, it'll say it's wrong when you tell it's wrong. So if you ask for something, it'll give you a response, and then you're like, hey, no, you're wrong. And it'll be like, you know what? You're right. I was wrong. And then, you know what? And then you could go back and say, you know what? You were right. And it'll be like, you know what? You're right. I was right. And so it basically is very agreeable, and it basically just tries to be nice to you, but at the same time, it tries to give you the answer with the most probability. And so sometimes it makes mistakes doing that. The last thing is if you have agentic workflows that are fully automated, as in end-to-end, it does it all. It receives data from maybe like a tool that has telemetry, and then it processes it, tries to determine if some process is malicious. So a system like that would be end-to-end. It would be fully autonomous. And in those situations, when you have prompts like, oh, user can't respond, do your best, sometimes when it doesn't know what to do, it just makes random shit up. It's like, hey, that user was doing something really, really fishy, and then when you go to investigate it, there's actually nothing there going on. And so what do we do now? If LLMs are good at things, but their scope is too small, and if they cause a lot of false positives, and if they don't find things you want, do they completely suck? Well, they would if you decide to run something like that. If you go to a large repository like Kubernetes, for example, and ask Claude, hey, find everything you possibly could, it'll try, but it'll do it poorly. And one of the reasons why it has no threat model, it has no attacker capabilities, it doesn't know what it's supposed to look for, what lens it's supposed to look at it from. So at the end, you end up getting a bunch of CW-ish vulnerabilities. The other thing it does is it gets pushed into like a breadth-first hallucination. And so basically, it'll have a super broad prompt that results in super broad answers. The model at that point will try going through files and basically look through snippets of code and try pattern matching that with whatever it thinks it knows. And you'll end up getting a bunch of theoretical vulnerabilities that sometimes might not even exist in your code base. It might even be looking for vulnerabilities that your code base would never be vulnerable to because of the languages it uses or how it's hosted or things like that. And so what that brings me are to guidelines for a solution. The very simple answer is to reduce scope when you're using these LLMs so that you result in less context rot, because over the period of time, if you feed it enough information, it would not know what to do. And then it would start hallucinating more, it starts giving you wrong answers, it can't keep it all in its brain. And so that's the first step. The other additional step is you could use a multi-agent workflow. And here's a very simple example that for the presentation. And in this case, we have a source to sink mapper, threat modeler, a vulnerability finder, and design docs and stuff. So I'll go over this really quickly, but pretty much you can, if you use something simple like this, you could have a source to sink mapper. So for that Helm situation, for example, you could map the entry point that we gave with the different sinks that you would be interested in finding. And so what it would do is it would just create a bunch of files with different same source to different sinks. Then you have your threat modeler where it will basically go through all these, look at the technology and say, hey, what's something an attacker could do? You could use Stride or any other methodology you want. You could also think of it from the lens you'd want to think of it as. Then something that I believe helps are design docs if you could parse them correctly, because sometimes you look at a code base and it might look like a vulnerability. Something simple like an iDrive, and it's like, hey, you can't cancel money or funds in another account that you own but then you read the design docs and you're like, okay, maybe you can. So sometimes you have to do that back and forth, and if the LLM already has this parsed and know how something is supposed to work, and then they look at the code base and be like, hey, maybe the developers didn't implement their design docs correctly, that might also lead to other vulnerabilities. And so when you take this structured approach and have specialized agents, you have one agent that kind of does what it's supposed to, and it doesn't have too many responsibilities, which then takes it and passes it on to the next agent. Also prompting. So with prompting, there's actually this research paper that came out which basically talks about, are the repository level config files actually useful for the efficacy of how well your agent does? And so it was found that if you write your prompt files poorly, and you're better off not writing them at all. If you write them poorly, it's actually going to reduce the performance of your agent and reduce task success. It also increases your cost by 20%, so you're just feeding and wasting money for no time. And basically what the behavior was noticed from this research study is that the agents become more verbose, and they become more, they explain things more. So they want to tell you everything that they know. But in doing so, they actually become less effective. And the root cause of this is they become more redundant, which causes them to overfollow constraints. If they already know something and you tell them that again, they're gonna do that twice than they normally would. And after that, it's gonna tell you how great of a job it did by listening to you, which is then gonna take more tokens and then cause more money issues. And so the other guideline other guideline I have is, unfortunately, you can't take an agent or an architecture or prompts from online and always put them into your code base and use them. And this is because there is no one style fix all solution. The thing that I noticed that really helps, as I mentioned earlier, are making good threat models. And so threat model is basically like a compression algorithm for what the agent is supposed to be looking for. And so if you take a threat model, you identify your trust boundaries, you have your high-risk operations that typically happen in your code base that you're aware of, whether that's like serialization or parsing or like ODZ or anything that touches the disk, anything that touches network, whatever that might be that you're more prone to, and you create a good one-page threat model with that and have your tier 1 microservices or your like crown jewel functionalities that your services offer, you're gonna have much more success. Additionally, when you have lesser invariants like, okay, admins can only reach X, or your JOT issuers must only be Y, you won't give it a lot of excessive information it doesn't need. This is a lot better than if you were to have a massive like 1,000+ lines of a skillmd file that would have every security checklist in the world. It would have all the boilerplate instructions. It's going to have a bunch of random things to follow, and over the period of time, it's not going to do anything well at all. And the other two things that I want to mention here is that when you have this, you make sure that your scope is as small as possible. So what I've noticed works is if you start with one entry point, that can either be an endpoint or maybe a really small file, and then you could have it try to trace all the different syncs with it. So that way it's laser focused on something so small that it becomes harder for it to mess up. And the other thing I'd like to add is make sure you have enough logging enabled so that even if you don't see the result, you see how the agent thought. So that way you could keep that in mind and use it to get to your end destination, whether that's finding a vulnerability or understanding the code base. And so I'll give a quick little, like, it's not really a demo, it's just like some sort of proof of what magic looks like. So if you guys remember the Helm vulnerability I talked about a couple minutes ago, I tried using that same setup really quickly, took maybe like half a day to build these agents, and then I send it through. So first path, if you see, I tried doing the Tate analysis in which I would gather sources and syncs, and I bunched them up, so I ended up getting about 20 or 30 different syncs it was hitting, and then one of them actually happened to be the exact sync that was required for this one to work, in which case the log file which it wrote to disk, so at least I got that down. And then I had a threat model which it was testing different possibilities. And so it found the right abuse case for the CVE, in which it was basically provide a directory that had files that were symlinked. So okay, now we got the fact that it writes to disk. Okay, maybe it could have a symlink. So surely the finding is going to be solid. The finding was, okay, it didn't do as well of a job. It got a read function rather than a write function. So it didn't necessarily find the best abuse case. So then I started thinking, okay, why didn't the agent put this together? It had a lot of information and it had a lot of data. And what I found is, I think while it was doing the threat modeling, I think it got social engineered by the code base. I think it read the code base and the code base said, oh, this is immutable. Like you can't do this. And the agent's like, you're right, I can't do this. And so that's what the threat model, it was part of the threat model's assumption that, okay, I cannot do this. And so did it work? I mean, maybe, maybe not, but somebody that has done security and is researching for these bugs, if they were to look at all these logs that are generated or the possible threat models that generated, it would help them get to the same endpoint. And so when you have something that is really large, it may not find all the bugs, but with enough verbose output, it could give you enough that you could put those pieces together and then get there. Just going through one entry point took an hour of Claude code running, which I thought was bugging out at some point, but it was just running. It spent about $5 per entry point per run. Opus 4.6 on the highest effort. And so it's like the lessons learned from here is that if you throw enough money at something, it might just work better. And so that's what Claude did for me, at least. But more seriously, it could save significant amounts of time on low-hanging fruits, so that if you looked at, for example, the very first pickle.loads example with 5,000 to 10,000 lines of code, it found that pretty quickly, it was a needle in a haystack, I guess, but agents are really good at doing that these days. But also it wasn't necessarily large enough that it was confused. And so since it's a simple pattern match, it's a low-hanging fruit. And if it's a low-hanging fruit, it could catch it pretty easily. To answer the question, are you worried? You probably shouldn't be this month at least. I mean, things change so quickly. Now what Cursor and Claude code do is to spin up agents for themselves. So that setup that I showed you is actually kind of like over a month old, what I submitted this talk originally. But what Cursor does now, and I like both for different reasons, but if you ask Cursor something to do, and it's complicated enough, it'll auto spin up, it'll do RAG by itself first, and then it auto spins up agents to then complete the task, and it creates its own sub-agents. It creates a to-do list actually, and the to-do list has its own sub-agents, and then it uses them, completes its tasks, takes the output, pushes it to the next agent, and it does this over and over again, and the efficacies of them have improved to the point where your prompts don't have to be super crazy. As long as you're running something that's small enough, it kind of works. And the last thing that you should think of is there's companies that do AI bug hunting for a living. Like they literally research this every day. And so if you've ever gotten a demo from them, I'm not gonna name any, but if you've ever gotten a demo from them, maybe you've seen how not awesome their stuff is doing and the things that you as a developer have to do for the product to work in your environment sometimes. And so if there were to be these companies that are released, that are doing an excellent job, that are finding all the bugs, then yeah, maybe you should probably be worried about your job. But for the time being, I think we are okay for maybe a couple months. But yeah, thank you. I hope you guys were entertained, or if you have any questions. Yes.